So I want to find the relative absolute, relative minimum and absolute minimum of this guy. So, well, let's just actually find the derivative and find out what it's gonna look like. Let's see, okay. So the derivative for this guy, let me see. Okay, so I have two guys being multiplied. So let me actually just use the product rule to deal with that. So it's gonna be the first 3/2 x to the 1/2, 1/3, times derivative of the second derivative of 2 plus x is gonna be 1, plus derivative of the first. So that's gonna be 3/2 times 1/3 times x to the negative 2/3 times 2 plus x. Okay, that doesn't look very nice. Let's see. The 3 cancel out. So I get 3/2 x to the 1/3 plus. Let me actually try to simplify this thing. Let me actually expand this guy out and let's see if something nice will happen. If I expand this thing out, 1/2 x to the negative 2/3 times 2, the 2 will cancel out. So I only have x to the negative 2/3 left. Plus 1/2 x to the negative 2/3 times x. X to the negative 2/3 times x is x to the 1/3. I can combine the term x to the 1/3, so I'm gonna be left eventually with, let's see, 2x to the 1/3 plus x to the negative 2/3. Now then, I need to solve for when this guy doesn't exist, for when it equals to 0. So let me actually simplify this a little further. Let me see. X to the 1/3 is the same as cube root of x. So this is 2 times the third root of x plus x to the negative 2/3 is the same as 1 over the third root of x squared. If I try to combine the two terms, I'm going to be left with, so the denominator is going to be the third root of x squared. So it's going to be plus 1 here. If I multiply the third root of x squared to the third root of x, I'm just going to get third root of x cubed. So that's going to be just x. So I'm going to have that this guy equal to x plus 1 all over third root of the x squared. So the critical number, that means I'm gonna need to solve for when this guy is 0 or when it doesn't exist. If a fraction equal to 0, that means the numerator has to equal to 0. And if 2x plus 1 equal to 0, that means x has to be negative 1/2. So that's my critical value, but that's not the only critical value because this guy, it may not exist. A fraction will not exist when the numerator, when the denominator equal to 0. And that's going to be when x equal to 0. Because when x equal to 0, this guy is going to equal to 0. I said I have 1 over 0 and that's not defined. So that's going to be my other critical number here. So this corresponds to when the derivative doesn't exist. So that's the two critical number. Now I need to find out whether these two guys are relative min or relative max of my function. So I have the two choices here. I can either use the first derivative test or the second derivative test. So usually you have the choice. You can use whatever that you feel more comfortable with. For this one, I don't want to find the derivative of this guy again, so let me actually just use the first test. So that means I need to find weighter on the interval. So I just need to find weighter when x is less than negative 1/2, and when it's between negative 1/2 and 0, and when x is bigger than 0, whether they are positive or negative. And when x is less than negative 1/2, you can kind of imagine my numerator is negative, but my denominator is positive. So this whole guy, when you divide negative number by positive number, you get negative number. Between negative 1 and 0, my numerator is positive, and my denominator is also positive. Actually, my denominator is also positive because x squared is always positive. So this guy is positive. And this guy, when x is positive, the numerator and denominator are both positive, so they are positive. So the 0 here, this guy is actually our false alarm. If you look at the graph that we plot earlier, that thing that we got, that actually corresponds to this vertical inflection point here. The tangent line here is vertical, so that's why this is a critical point. So that's why the thing shows up there. But it turns out to be neither relative min or relative max. Now, if you were to sketch the graph of this guy, I mean without sneak peeking at the graph, your function should be decreasing over here, increasing over here, and keep increasing. Something funny happened here. We see from the plot, we can achieve that it is a vertical line inflection point, but let's say we don't know. But this is the sketch of the graph so far. So that means I can tell now that my function has a relative min at x equal negative 1/2. And because this guy, well, it keeps coming down until this guy and then it goes up. So this is the only possible relative min, and it also has to be absolute min. So which is also. So there's no way I can go lower than this point. So this guy is the absolute min. On the other hand, my function just keeps going on both sides. So that means my function has no absolute max. I mean, has no relative max. So remember the extreme value theorem said that the absolute min-max exists if my function is defined on a closed interval. However, if you are talking about the real line, then the absolute min and absolute max, it actually may not exist, which is actually the case here. You have the unique absolute min, but there is no, relative min, but absolute min, but there's no absolute max. So there is no relative max, and there is also no absolute max. Now then, there is one more thing I have left to do. The question also asked me to find the inflection point. So unfortunately, it seems I'm gonna have to find the second derivative. So I need to find the second derivative. So that means I need to find the derivative of this guy. But they are all equal, so I can just use the one that I think is gonna be easiest to find the second derivative. So you can find the second derivative from here, but you will have to use the quotient rule, and that's gonna be a little bit more work. So I'm gonna have to go a few steps back. So I'm gonna use this guy to find my second derivative, because it seems like this guy is simplified enough for me to find the second derivative. So the second derivative is gonna be, let me see, it's gonna be 2 times 1/3 times x to the negative 2/3. Okay, my other term is gonna be negative 2/3 times x to the negative 5/3. Okay, so that's my second derivative. Let me simplify that. So let's see, I get 2/3. I get 2/3. Let me see, 1 over third root of x squared minus 2/3. 1 over third root of x to the 5th. Okay, this one still doesn't look very nice, so let me simplify that a little further. I can pull out the factor 2/3, so that makes life a little simpler. And then my common denominator, that's going to be the third root of x to the 5th. And that's going to be minus 1 there. Now then, to make the third root of x squared, third root of x to the 5th, notice that this term is actually just the third root of x squared times x. So this whole thing, let me actually write it as a side note here. So 1 over third root of x squared is the same as x over third root of x to the 5th. So that first term becomes just x. So my second derivative is equal to 2/3 of x minus 1 over 3 times x to the 5th. So that means, once again, my second derivative is 0 or it doesn't exist when x equal to 0 or 1. Because that 0 is when my numerator equal to 0. And 1, the 1 is when my numerator equal to 0, and 0 is when my denominator equal to 0. And that's where my derivative doesn't exist. And if I do what I usually do, once again, I plot the graph for second derivative. When x is less than 0, this guy is negative, and this guy is also negative. So negative divided by negative, you get positive. If x is between 0 and 1, the denominator is positive. If x is between 0 and 1, the denominator, numerator. Okay, I keep getting this mixed up. Okay, let me say this one more time. When x is between 0 and 1, the numerator is going to be negative, but the denominator is positive. So the whole thing is negative. And when x is bigger than 1, both numerator and denominator are positive. So it's positive. So my second derivative actually changed sign at 0 and 1. So that means my function has an inflection point. I mean has inflection point. When x equal to 0 and 1. So if we look at the graph that we kind of have earlier, this is kind of what's going on. You have your function concave down, your function concave up, and then it concave down a little bit, and then when after x equal to 1, it actually concave up again. So that one is a little hard to spot using the eye, but you actually have another inflection point here. So without algebra, it's going to be quite hard to identify that inflection point. Oh, and by the way, now that we have found the second derivative, you can actually use the second derivative to test if these two guys are relative mean or relative max. If you plug in -1/2, you'll see that the second derivative is positive. And that makes sense that it was a relative mean that we have found earlier.